Yeah, hi, this is Vinay Kumar Reddy Vempelli. Today I'm here to explain about uh, my project. Here in the first thing, I use the data report of cat versus dog image classification data set. So I took this data set from official website of Kaggle. So we can download it from the above website. So this basically the data set consists of 250 25,000 labeled images of cats and dogs. So it is evenly split with 1 lakh 12,500 images of cats and 12,500 images of dogs. So images are in various formats and resolutions. So I have data set. This I divided this data set into like two sets, like training set and testing set. So in training set, we have 20,000 images, and testing we have 5,000 images. So if you see the overview of this data set, like is widely used for deep learning. This data set is widely used for deep learning, so for binary image classification tasks. So it serves as a benchmark for beginners and researchers interested in image recognition and computer vision. This dataset is popular for practicing and developing convolutional neural networks, which are popularly known as CNNs. So why we are choosing this dataset? Because this why I choose this dataset for final project, because it provides a straightforward and widely recognized problem of distinguishing between cats and dogs in images. So it's a suitable choice for demonstrating the application of deep learning techniques for image classification tasks. So the report conclusion gives, so the cat vs dogs image classification is readily available and well labeled data set that can be effectively used for deep learning experiments. So its simplicity makes it a suitable choice for showcasing TensorFlow based CNN models and training in the final project. So I I also downloaded the modules for update in C for 10 data sets. So I download all these 10 data sets from the canvas, and I make them into one data set, which includes both training and testing data. So first, to upload these data sets to remote virtual machine using SSH, I followed these few steps. I opened a terminal on my local computer, and I used the SCP command to copy the dataset to remote virtual machine. Here is the command I used. So I was promoted to enter the password for the remote virtual machine. I entered the password to initiate the file transfer. I ensured that I created a new subfolder named CIFAR underscore 10 underscore data under the JP notebook directory on the remote virtual machine. I upload all the downloaded CIFAR 10 dataset files to the newly created CIFAR data 10 data subfolder on the remote instance. In this section, I successfully obtained the C410 datasets by downloading the required dataset files from the Canvas module, and then I transferred these files to the remote virtual machine on GCP, where they'll be used for deep learning research and training. But so now I created a design of a CNN, which is known as convolutional neural network. I have designed a CNN model for 10 C for 10 dataset. The architecture of the network will be as follows. So there will be input layer. So this input data is not reshaped, and it is directly fed into first convolutional layer. This layer one has 32 filters, and the filter size is 3 into 3, and the activation function is ReLU, and max pooling is 2 into 2. And the second convolution layer is has 64 filters, and the size is 3 into 3, and activation function is ReLU, and max pooling is 2 into 2. And um, the fully connected layer has it has 128 neurons, and activation function is ReLU, and fully connected layer is like output layer, which is known as an output layer. So it has number of neurons is 10 for 10 classes, and activation function is softmax. So here for inputs I use the activation function as ReLU, and for output I use the activation function softmax. So for building and training and testing the model, I use the Jupyter notebook. Sometimes so uh, if you see, the code was similar to the use that minced data set, with the only difference being that the input data was not reshaped. So I trained the model with 5,000 steps and tested it every 100 steps of training. During each testing phase I collected accuracy data to evaluate the model performance. So if you see the test for the results of training, so at 100 steps the accuracy is 55.3. Again, after 200 steps the accuracy is 62.1. After 300 steps the accuracy is 66.5. After 400 steps the accuracy is 69.2. After 500 steps the accuracy is 71.8. After 1000 steps the accuracy is 78.4. And if you go on 2000 steps it's 84.2. After 3000 steps it's 87.1. After 4000 steps it's 88.9. After 5000 steps it is 90.5. So the testing result shows that the CNN model trained on CFR achieved an accuracy of 90.5 after 5000 training steps. So this indicates the model performed well in classifying 32 into 32 color images into 10 different classes. The training accuracy improved steadily with more training steps. And then the other data set I used for is MINS data set. So, uh, so it used for a calculated mean accuracy and standard deviation for both data sets to compare their performance. So for MINS dataset, the mean accuracy is 98.7% and standard deviation is 0.5%. And for C410 dataset, the mean accuracy is 72.3% and standard deviation is 1.2%. So the performance gap between CNN models on the MINS 10 CFR10 datasets can be explained like because of their data complexity. So C410 is considerably more complex than minced. C410 contains 32 into 32 color images with 10 diverse classes, while minced contains grayscale 28 and 28 images with only 10 digits. The increased complexity of the object recognition in C410 poses a greater challenge for the CNN. So, and also image variation. C410 images exhibits variation in object orientation, lightning conditions, and background clutter. These variations make it harder for the CNN to learn and generalize compared to the simpler and more uniform minced images. And there are also model architecture. So the CN architecture used for both datasets may not be optimized for C410. While it performed exceptionally well on Minst, its ability to capture complex features in C410 may be limited. So fine tuning the architecture or using more advanced models could potentially bridge the performance gap. And another thing is training data. So Minst contains large amount of training data related to a number of classes, facilitating better generalization in contrast to uh, say for 10 fewer trainings, samples per class, making more prone to overfitting. So the performance gap between the CNN model and Winston CFR is primarily attributed to dataset complexity, image variations, and model architecture. Further optimization and exploration of advanced CN architecture may lead to improved results on C410 dataset. So here for enhancing CNN performance on C410, so we need to enhance this performance on CNN of the C410 dataset. The primary objective is to close the performance gap between the C410 and means data set and achieve improved accuracy and generalization. So where in which areas we need for the improvement? One, there is model complexity. So observations. So the current CNN architecture may lack the necessary complexity for the CFR10 data set. So for this, what I am going to do is we need to augment the model's complexity by introducing additional convolutional layers and increasing the number of filters to enable better feature learnings. And at the same time, regularization techniques. So, overfitting may contribute to lower performance on C410. So, for this, I am proposing like we need to implement dropout layers to address overfitting and particularly after the fully connected layers. This step will encourage improved generalization and learning rate schedule. So their learning rate schedule rates used during training may not be optimal for convergence. So we need to adopt the thing I am proposing for this is we need to adopt a learning rate schedule that gradually reduce the learning rate as training progress. This approach can lead us to improved convergence and fine tuning. And another thing is data augmentation. So C410 emergence exhibits variations in orientation, lightening, and background clutter. So we need to apply data augmentation techniques to the training data set, including random rotations, scaling, and horizontal flipping to enhance model robustness against variations. So for these methodologies, so for model modification, we need to implement the proposed architectural changes in the CNN model, including additional convolutional layers and dropout layers. And learning rate schedule, we need to integrate a learning rate schedule that reduces the learning rate by a predefined factor after a specific number of training steps. Data augmentation. So we need to apply data augmentation techniques to see for 10 training datasets using TensorFlow data augmentation utilities. So after performing all these things, what are the expected outcomes we are getting is after implementing these things, we retraining the CNN model on the C4 dataset and we anticipate the following results. One thing is to improve the accuracy and generalization on C410 potentially closing the performance gap between the mixed dataset, enhanced model robustness to image variations and complexities, mitigated overfitting, resulting in improved generalization. And so the final project, what I've done is aim to explore deep learning with CNN using TensorFlow, focusing on the C for 10 dataset. This report summarizes the work completed in different project parts and the conclusions drawn from the experiment. In this final project, I conducted several tasks across different parts. I designed a CNN architecture of C10 with two conventional layers and two fully connected layers. Using I used the Jupyter notebook, loaded them, and pre-processed and trained the model for 5,000 steps. I tested every model every 100 steps and recovered the accuracy. I compared the performance of CNN models on the days minced and C for 10 datasets. I calculated mean accuracy and standard deviation for both datasets. I provided the explanations for the performance gap observed, and I also proposed changes to enhance the CNN performance on C for 10, include increased model complexity, regularization, learning rate schedule, and data augmentation. I outlined the methodology for implementing these changes. And also, I introduced the project and summarized the work done in all the project parts. I provide conclusion drawn from the results of testing the CNN models across different project parts. So, from the results and observations in different project parts, several conclusions can be drawn. So, the designed CNN outputs of C10 show promising results, achieving an accuracy of 90.5 percentage accuracy after 5,000 training steps, and a significant performance gap exists between CNN models and on the means and C for 10 datasets, primarily due to dataset complexity, image variations, and model architecture. And proposed improvements in part 4, such as model complexity, regularization, and learning rate scheduling, and data augmentation, hold the potential to bridge the performance gap on C for 10. So the final project provided valuable hands-on experience in deep learning with CNN using TensorFlow. It showcased the importance of dataset selection, model design, and critical thinking in addressing challenges in deep learning tasks. The final project report summarized the journey and sets the stage for further experiments and improvements in CNN performance. Now, if you go look for a code, so first I give the path of the dataset C for 10 and it's a zip file, and I unload using unpickle. I unloaded the dataset with batches like batches data batch 1, data batch 2, data batch 3, data batch 4, and then I loaded all the data. And if you see the batch names, label names, we have automobile, boat, cat, deer, dog, frog, horse, sheep, truck, and everything. So, and then what are the keys we have? Directory keys, and then for graphs, use matplotlib as a PLT, and I also imported numpy as a NP. Now we're getting X data batch 1. We're getting the batch one data, only if you're getting data and we reshaping it. So it's a 10,000 files with 32 transpose into unit int 8, and we're getting max value 255, and we are dividing the 255, we get 1.4, and we're showing that image using plot matplotlib. We'll get one image, and we're getting another one second image and another x of 4. Randomly we're selecting few things and we're getting images. So using to use one hard code 10 possible labels, we are using this on hard format. And then so make it ready for first you are creating layers here. We are defining a class and we need to train all the data sets: batch 1, batch 2, batch 3, batch 4, batch 5. And we're creating a test batch as well. So it's a test batch. So initially we are training image is equal to none, training labels is equal to none, test image is equal to none, and test labels is equal to none. And then we're creating setup images. So for we're now here setting up for training images and labels. So and then we're creating training images like from NumPy, using all 10 batches. So here all 10 batches comes from data batch 1 and data batch 2, data batch 3, data batch 4, and data batch 5. So we'll train training images. At the same time, we are reshaping them with 32 pixels, and we're transposing them and we are dividing it to 55. At the same time, we were training labels using one hard code. Now we are setting up the test images and labels. So test images will commit from test batch. So we are giving the test batch and we are reshaping them. Test lens with the 32 into 32 pixel, transposing them and slash 20 to 255. Now next batch. So here you're defining X as the training images. So it's reshaping it into 10 into 32 into 32 by 3. And we are training labels with batch size. And we are written X and Y here. Now we're calling ciphertext image. We are setting up image. So before using these two lines, we are just setting up labels and setting up test images and everything. Now, if you see, now we are defining the CNN model of the architecture. So here, okay, first input layer. So X is equal to TF load 32, shape 32 by 3, and Y true, it's something like placeholder like TF32 none button, and we are creating a convolution layer 1 using conv1 TF layers dot con 2D. Input is equal to X and filters is equal to 32. We have, as we said, we created 32 filters and kernel size is 3 comma 3, and its activation is a relu function. At the same time, we have pool 1. So for convolution layers, we have convolution layer and pool. We're creating the layers as well for pooling also. And then for convolution layer 2, we're creating again. For this, the input should be pool 1. For convolution layer 1, the input is equal to X, that is input layer. And for the convolution layer 2, the input is pool 1 and it has filter 64, the same kernel size 3 comma 3, and the same activation function relu. And the pool 2 is tf.layers.max pooling 2D. Here the input is conv 2 and pool size is 2 comma 2 and strides is equal to 2. Now we are flattening the output from the conventional layer. Now we are flattening the output with a single line. So flat equal to reshape pool -1 into 8 into 8 into 64. Now we are connecting the fully layers. So FC1 fully connected layers is equal to inputs is equal to flat. Here we has a flat and units is equal to 512 and the activation function is relu. Now for getting the output, we are getting the output layers. So logits is equal to tf layer dot dense and inputs is equal to FC1. This is a fully connected layer and units is equal to 10. And then we're returning x and y true and logits. And we are also creating another training function. So CNN model based on X, Y true logits, and with he getting for better performance, we are creating a learning rate equal to 0.001 and number of epochs is equal to 10 and batch size is equal to 100. Now we define the loss function. So cos entropy is equal to TF reduced mean software entropy with logistics. Labels is equal to y equal to true and logic is equal to logits. And we are defining optimizer. So we here training Adam optimizer and we're training optimizer with cross entropy and we are computing accuracy with correct prediction TF equal to equal argmax with logistics 1 and argmax ty equal to 1. And also accuracy, to get accuracy we are creating tf to reduce mean, tf cast correct prediction comma and tf float 32. So we are creating a session here. So with the tensorflow session is says and then we are running initializing the thing uh, and for each epoch in a range of number of epochs, a number of epochs is 10 for us. So for epoch in range of number of epochs like it's 10, it will keep on changing the batch size and train the sessions and it will train the thing and it will train the images of everything and then we calculate the accuracy of each test after each epoch like we'll get some 10 he since our epochs is 10 we'll get the accuracy for each 10 epochs like each training set. So like that you'll get from 10 things. So the test accuracy is come you can get from the session run. So and we are printing the like we're printing the which epoch and what is the test accuracy of that. And finally based on not these 10 and again we're getting the final model accuracy as well. And it will get by using these two formulas like these two codes. And then we are creating the CNN model. So x comma y comma 2 logics is equal to create CNN model. That creates CNN model. I think we already created that function. So based on those things, based on these things, again we'll create the CNN model and the data set we'll set up and we'll train the model. Now we're building conventional networks. So again we're importing TensorFlow as TF and we're reshaping we're not reshaping we don't need to reshape the data here. So we're not reshaping anything and then we're creating any another same as we're creating a CNN model function and then we're training the things. The same thing is going to happen here as well. We're going to train the models of the phase 2 and we're going to get the results like we're going to get the results of each training set of how much it is and we'll train each data set each set uh, and we use the relu function here and you'll get the you'll bring the fully connected conventional layer and you'll get the results as you shown as you see the results you will get at 5,000 observations we got it as so at 10 epochs as you create a 10 epochs. So at 5,000 steps, you got a 90.5 accuracy, which is very good. It's a good thing we achieved here. Yeah, that's all about my project. Thank you.